Hi goers, so today we're going to finish up the Chapter 1 review videos by talking about resonance, the final topic in this chapter. So resonance is basically this theory where electrons in a molecule can be delocalized over a broader region, and in doing so we can get several different contributing structures, and no single contributing structure is the true structure of that molecule. What resonance theory states is that really the ideal molecule is a combination of all of those contributing structures. So with all these questions that you'll see on this worksheet, this is just one proposed structure for that molecule, but in theory there could be multiple different ways that you can write this structure, and the truest one, or the truest form of that in nature, is a combination of all of those. And just like everything, there can be some that are better than the others, and we're going to see which contributing structure is better, and if it is better, it contributes more to the overall general picture of that molecule, if that makes sense. Okay, so let's just start right in with, these problems. So with question number 1, we say that we have two other contributing structures. So none of these lone pairs are drawn in for us. So we know that the oxygen bonding pattern is going to be 2 bonds and 2 lone pairs. So I'm definitely going to draw in those lone pairs. And then whenever I see negative charge, I'm assuming that's going to be a source of electrons. So there's definitely going to be a lone pair there as well. So in order to get my two other structures, I wanted to show you that whenever we have these carbon-oxygen functional groups, or these carbonyls, it's a good idea to resonate those pi bonds out, okay? So let's draw the resulting structure after that. And some people are kind of confused on why I put a negative charge on the oxygen and a positive charge on the carbon. So you can do the formal charge formula, which is formal charge equals the number of valence minus the number of sticks minus the number of dots. Okay, so you can do that formula each time, or you can rationalize, I took electrons from that pi bond and put them on the oxygen. Well, electrons are already negatively charged species, so by putting more negative on the oxygen, that's why it gets a negative formal charge. When I took those electrons away from that carbon, I took negative away from that, so that means it's going to become positive, okay? So you could also just do the formal charge formula each time, or you can use a little bit of logic to get there. So then my next step is going to be from a source to sink. So I already touched those lone pairs on the oxygen, so let me touch those lone pairs on the carbon and see if I get a different structure. So I can definitely resonate into the left because there's an electron deficient carbon, so the resulting structure of that is going to be something that looks like this. Okay, so these are my 3 resonance structures, and the overall resonance structure is going to be a combination of the 3 of those. Okay, so whenever I see carbonyls, or the carbon-oxygen double bonds, I like to resonate those out first because that gives me a positive local charge on that carbon, and then I can use that negative source of electrons and push those in to fix that electron deficiency. Okay, so there are many different ways you can do resonance, and that's why most students have trouble with it, because another valid move for resonance was, instead, I'll just write it over here, I could have just done this move all at once, because I resonate those lone pairs in to form a pi bond, but I exceed the octet at the carbonyl carbon, and I have to push those pi electrons up. So then, the resulting structure would have been something that looks like this. And you see how I went from the first structure over here to the last structure without showing that middle structure. So that's why I like to touch the carbonyls first, just so you don't miss a structure. But that is also a valid move and totally correct. However, if we asked for 2 structures, you would have lost points because you didn't show that middle structure. Okay? So that is resonance for the first molecule. So again, we're going to look at this molecule over here. We see that we have these 2 oxygens, so let me just draw in these lone pairs. And I see that carbonyl again, that carbon-oxygen double bond, so my first move is going to be to put those pi electrons up on top of the oxygen. Okay, and we're going to touch the electrons, or the source of electrons that we haven't touched yet, so we're going to take those lone pairs and push them in. Those are my 2 other structures, and that's it. Okay, let's move on to number 3. So I said, hint, be careful. So the bonding pattern for nitrogen is 3 bonds and 1 lone pair. So we see that we have this 1 lone pair, and maybe those can move somewhere. So let's think about pushing those down. So the resulting structure would be something that looks like this. Okay. Can I do that? Well, if you said no, that is totally correct. You cannot do this because what happens is that there's an imaginary hydrogen here. So if I were to resonate those lone pairs in, we're exceeding the octet because that hydrogen would still stand. So that means we have 10 valence electrons on a carbon, and that's totally not possible. So you have to be careful with those imaginary hydrogens in line angle formula because there's no resonance with this structure. Okay? Let's move on to this one. So I see that this is a lactone functional group, and I see that carbonyl again, that carbon-oxygen double bond. So my first move is going to be to put those electrons on the oxygen. And the resulting structure would be something like that. And let's touch the source of electrons we haven't used yet and push those in to fix that deficiency. Oops, excuse me. And those are my two resonance structures, okay? So then finally, let's talk about a situation where we have a benzene ring. So benzenes have a lot of pi bonds in it, so that's why we see we have 4 other structures. So let's start with the source of lone pair electrons on that nitrogen, so we can resonate those into the left. Why can't I resonate it to the right? If you can't resonate it to the right, because we already have 3 imaginary hydrogens there, so by forming a double bond right here, you actually have 10 valence electrons on that carbon. So that's why we have to go into the ring. So if I were to push them into the ring, I form a double bond there, and then I would technically exceed the octet at that carbon. So that means I have to do a second move, meaning I'll push those pi electrons and make them a lone pair. Okay? So this is a very important thing that I want to point out right here. When you exceed the, you typically do one move at a time unless you exceed the octet. So in this situation, we did one move by putting those lone pair electrons on the nitrogen in to form a carbon-nitrogen double bond. But since we exceeded the octet at that carbon, we had to push those pi electrons out. Now, there's another point I want to make. When we have this choice of making a pi bond into a lone pair, it also could have been possible to do this arrow, pi bond to pi bond. But by doing pi bond to pi bond, I have to force this pi bond out. And then by doing that, then I probably have to force this pi bond out. So you can see by doing pi bond to pi bond, you miss a whole bunch of other structures that are possible. So that's why you typically want to do one move at a time unless you exceed the octet, and also pi bond to lone pair when given that choice. So that's why I'm putting it on this corner. So the resulting structure of that would look something like this. Okay, so then let's use that source of electrons, those lone pairs, and keep going around the ring. So I can do lone pair to pi bond, and then this pi bond can turn into another lone pair because I exceeded the octet again. Okay, so then you can just keep pushing around the ring. So put that as double bond, but we exceed the octet, so we have to do a pi bond to lone pair arrow. Okay, and then we can keep going around the ring to get our last structure. So by putting those lone pairs in to form a pi bond, we can push those pi electrons back out onto the nitrogen. And the resulting structure of that would look something like this. So some students are like, isn't that last structure the same as the first one? Well, no, because look at how the pi bonds changed positions. So over here, they're in this location, and then over here, they're in this other configuration. So these are my 4 other structures. So again, benzenes can be a little bit complicated because you don't want to skip any other structures. So basically, it's one move at a time unless you exceed the octet, and when given the choice, I would do pi bond to lone pair every time instead of pi bond to pi bond. Okay? So that's pretty much how you do resonance. It's pretty easy. So let's move on to, these other types of problems. So again, like I said, there are many different ways you can do resonance, and they're all valid. But if we gave you a situation where we wanted to see all contributing structures, you would follow the guidelines that I said above. So in this situation, this is just showing the results of these resonance arrows. So this is one possible method of showing resonance. So if I wanted to draw the end product of that, it would be, so let me just label these carbons. Maybe it'll help you over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the lone pair electrons that are on carbon number 3 became a pi bond between carbon 3 and 4, okay? And then that pi bond between 4 and 5 became a lone pair. Actually, no, it looks like it became a pi bond between 5 and 6, okay? And then that carbonyl, that pi bond, became a lone pair on that oxygen, okay? So if you guess that structure, you're correct, okay? And then for number 7, let me label that again. 1, 2, 3, 4, 5, 6. So if I were to draw that out, basically that lone pair on carbon number 5 became a pi bond between 4 and 5. Okay? And then that pi bond between 3 and 4 became a pi bond between 2 and 3. And then that pi bond on the carbonyl became a lone pair on the oxygen. Okay? And that's that simple. Okay? So let's move on to these other types of questions. So now we have 2 proposed structures. So what are the resonance arrows to get from the structure on the left to the structure on the right? Okay, so let's just throw in those lone pairs there that are on the nitrogen. So clearly it looks like we formed a carbon-nitrogen bond over here. So the only way to do that would be to resonate those lone pairs to the left, but I exceed the octet at that carbon, so instead of doing pi bond to lone pair like I'm wired to do, I can just do pi bond to pi bond, because that's this one over here. And then clearly you see that we have a negative charge, so now we could do pi bond to lone pair. So those are my 3 sets of arrows to get to those structures. Okay? So finally, let's do this example. So you see that we have 3 pi bonds in this benzene ring, and it became 2 pi bonds in the benzene ring, and it looks like we gained a carbon-nitrogen bond. So the only way to have done that would be to move this pi bond over here. And in doing so, I exceed the octet for that nitrogen, so it looks like this oxygen over here gained another negative charge. So that would be the second arrow I would do. All right? And it's that simple. So finally, let's just do this applied problem. So for the following molecule, draw all the contributing structures, and B, circle the major contributor, and C, provide a rationale for why it's the major contributor. Okay? So whenever I see that carbonyl, well, let me just draw on these electrons first. Whenever I see that carbonyl, that carbon-oxygen double bond, I told you a good practice is to resonate those up. So the structure resulting from that would be something that looks like this. Okay? And then we're just going to start from the source of electrons, so maybe the lone pair on the nitrogen, and then we're just going to move around the ring and see what happens. So I can take these electrons and push them here to make a pi bond, but then I exceed the octet there. So then I'm going to do pi bond to lone pair. Okay, so that's this structure resulting from that. And then I can keep going up and push those lone pairs on to fix that positive charge that was there. So then the resulting structure of that would be something that looks like this. Okay, so that is the resulting structure. Those are all the possible things that I could have done. There's nothing else I can do. So now we have to decide what is the major contributor. So the major contributor is the structure that has the overall greater contribution to the resonance hybrid. And then there are 4 sets of rules that we're going to go by. So number 1, Octet Rule. Number 2, minimizing formal charge. Rule number 3, charge separation. And rule number 4 is that formal charge on the most electronegative atom. Okay? So we're just going to go down that list of criteria and, see what's satisfied. The first thing is the octet rule. Well, let's just label these structures. So A, B, C, and D. So A, yes, we satisfy the octet rule, definitely a contender. B, we don't satisfy the octet rule because this carbon is electron deficient. See, that's a positive charge there? So that means that this one cannot be the major contributor. For C, we see that we also have that carbocation right here. So that's also an electron deficient species. It violates the octet rule. So nope, that can't be the major contributor. And D is good with the octet rule. 2, The next thing is minimize formal charge. Well, you see on the molecule for labeled A, there is no formal charges, but on molecule D, there are formal charges. So clearly, that is the rule that was violated, so structure A is going to be the major contributor. So you would just say, structure A is the major contributor because we minimize formal charges. All right, and that's pretty much all that there is for resonance, so just follow those guidelines and you'll be golden.